Welcome to the Explainer. Every single year, literally billions of tons of aggregate, asphalt, and concrete are meticulously engineered and laid down all across the globe to build something we often take completely for granted, roads. They are, without exaggeration, among humanity's greatest engineering achievements. They connect our communities, they facilitate global trade, support economic growth, and literally shape the development of entire nations.
But let me ask you, have you ever actually wondered how roads are built? How often do we consider the intense, microscopic battle of chemistry and physics required to lay just a single mile of modern highway? Because it's definitely not just about pouring some black or gray material on the dirt and calling it a day. No way. Behind every single stretch of road lies this hidden world of high-stakes engineering, meticulously planned sequences, and incredibly rigorous quality control. So today, we're going to peel back the layers of our daily commute and reveal the extraordinary science of pavement construction.
Okay, let's dive into this. Here is our agenda for the journey. 1. Preparing the ground. 2. The flexible pavement path. 3. The rigid pavement path. And 4. Pathways to progress.
Section 1. Preparing the ground. The universal foundation of all roads. Before we even think about the surface you drive on, we have to prepare the earth itself. And this requires a much slower, very deliberate approach, because absolutely everything built above it relies entirely on the strength established right here in the dirt. Think of this process kind of like a high-stakes baking show, but for industrial manufacturing. Every single layer has to lock perfectly into the next. Step 1 is survey and site preparation. Engineers use GPS and total stations to map out the exact alignment and drainage, completely clearing the area of any unsuitable soil. Then we hit Step 2, subgrade preparation. This is the natural earth. Excavators and graders shape it out, and then heavy rollers aggressively fight any weak spots, really compacting that soil down until it exceeds 95% of its maximum dry density. Once the earth is locked in, we add Step 3, granular subbase construction. Acting as a crucial drainage layer, aggregates are spread out, sprinkled with water, and hit again with vibratory rollers. Finally, Step 4, base course construction. This is the layer that distributes the wheel loads down into the earth. Often engineers mix aggregates with water in a highly controlled plant before massive pavers spread it perfectly flat. Only when this foundation is flawlessly smooth and incredibly dense are we finally ready for the surface.
Moving to Section 2, the flexible pavement path, building bituminous roads. From our perfectly prepped base course, our construction path actually diverges. We're going to head down the first specific construction method, building a flexible asphalt road.
Now, what's really interesting about this slide is that keyword flexible. Bituminous pavements are known as flexible pavements because they can actually yield slightly to traffic loads. It's pretty amazing. They're constructed using hot mix asphalt, which is highly cost-effective, provides a very comfortable ride for us drivers, and allows for stage construction over time. But hey, don't let the cost-effectiveness fool you. These roads demand absolute precision engineering, especially since they do require periodic maintenance throughout their lifespan.
The process here is a highly specific chemical and physical recipe. Step 1 is the prime coat. A bitumen distributor sprays a binder over that granular base we just built, penetrating the surface to bind any loose particles. Then comes Step 2, the tack coat. This is a thin spray of emulsion that acts as an absolutely essential glue. It creates a powerful bond between the existing base and the brand new bitumen-y layer. Without this glue, the pavement layers are under an active threat of slipping and failing prematurely right under the weight of traffic. Once that glue is down, we move to Step 3, hot mix asphalt production. In a massive mixing plant, aggregates are dried and heated while bitumen is heated separately. They're combined under strictly monitored temperatures. If it's too hot, the binder gets damaged. Too cold, it simply won't compact.
Once that perfectly heated mix is laid down by the paver, we enter the compaction phase. And there is a magic number here, 3. There are exactly 3 stages of rolling. First up is the breakdown rolling, using heavy vibratory rollers right behind the paver. Second is intermediate rolling with pneumatic tire rollers to really knead the asphalt together. And finally, finish rolling using tandem rollers to smooth the whole thing out. The timing here is a total Goldilocks scenario. It has to be absolutely perfect. The mix must remain within a very specific temperature window. If you don't roll it enough, the pavement life is drastically reduced, but if you roll it too much, you'll actually crush the aggregate structure inside the road.
And we definitely don't just guess if we got it right. Before a single car is allowed on this road, it goes through a rigorous final testing phase. Engineers conduct core density tests, they verify the exact thickness, they check for surface evenness, and they even verify the specific bitumen content in the mix. It really reinforces the idea that this is a highly controlled science. We aren't just throwing hot rocks on the ground and hoping for the best.
And this brilliantly illustrates our transition into Section 3, the rigid pavement path. Heavy-duty concrete. What if we need something built for extreme, punishing wear and tear? Well, we shift gears to the heavy-duty concrete road. Picture your local international airport runway, or maybe a massive commercial port, or even the most heavily trafficked intersection in your entire city. These are known as rigid pavements. They derive their immense strength from Portland cement concrete slabs. Now, unlike that flexible asphalt that yields slightly, this rigid structure distributes heavy wheel loads over a much wider area. The initial cost to build a rigid pavement is generally a lot higher, but they have significantly lower maintenance needs. That makes them an absolute necessity for those heavy traffic zones where you literally cannot afford constant closures for repairs.
The construction of a rigid pavement is a beautiful exercise in meticulous geometry. Step 1 involves setting up the forms and guide rails to establish the exact shape and dimensions of the slab. Step 2 is critical, placing the steel. Dowel bars are installed across the transverse joints to transfer immense loads between adjacent slabs, while still letting the concrete expand and contract. Tie bars go along the longitudinal joints to literally tie the lanes together so they don't drift apart over time. Then, Step 3, concrete placement. These massive machines called slip-form pavers receive the concrete mixture, which is this highly precise batch of cement, water, fine, and coarse aggregates, and they continuously spread and shape the pavement in one smooth, continuous motion.
But laying the concrete is only half the battle. Engineers then have to wage an active battle against internal flaws. As the concrete is placed, internal vibrators are submerged right into the mix. This is called consolidation, and its sole purpose is to shake out any entrapped air and achieve maximum density to eliminate weak spots. And, because concrete naturally expands and contracts with temperature changes, it's inevitably going to want to crack. So engineers beat it to the punch. They perform precise saw cutting at exact intervals to create joints. This dictates exactly where the road is allowed to crack in a controlled manner, preventing random, destructive fractures all across the surface.
So the crucial point here is a slightly counterintuitive secret: curing. You might think the goal is to dry the concrete out as quickly as possible, right? Actually, scratch that. It's the exact opposite. Curing is a race to trap moisture inside the slab. The ultimate secret to achieving maximum concrete strength is holding that water in to promote chemical hydration. If the water evaporates too quickly, the concrete will end up weak and brittle. So engineers trap this moisture for several days using water curing, wet coverings, or by spraying a specialized white membrane curing compound directly over the fresh surface.
Just like our asphalt roads, rigid pavements face intense scrutiny before commissioning. We're talking strict laboratory hurdles, slump tests to check workability, compressive and flexural strength tests where they physically crush concrete samples to see what they can take, thickness verification, and rigorous surface smoothness checks. This absolutely matches the intensity of the asphalt tests and definitively proves that these massive concrete slabs are evaluated down to the literal millimeter before they're finalized. Let's move to Section 4, Pathways to Progress, Choosing the Right Road. Let's see how this builds our complete understanding of modern infrastructure as we bring both of our construction paths back together.
So, why does an engineer choose asphalt over concrete? Well, if you need a lower initial cost, a really comfortable ride, and the ability to build the road in stages over time, you go with the flexible, bituminous path. You just have to accept that it's going to require periodic maintenance. But if you're building that airport runway or major commercial port where the physical loads are just immense and maintenance closures would be incredibly disruptive, you invest in the higher initial cost of a rigid concrete pavement. It will distribute those heavy loads over a wider area and stand up to the punishment for decades with very little upkeep. Both of these recipes rely on that universal, perfectly compacted dirt foundation we talked about, but they elegantly solve very different engineering challenges.
Whether flexible or rigid, the successful construction of a pavement is an incredible story of teamwork, dedication, and exact science. Understanding the massive effort, the relentless testing, and the heavy machinery required gives us all a profound new appreciation for the extraordinary civil engineering hidden right beneath our tires. As our source material beautifully states, roads are more than infrastructure. They are pathways to progress. But as climate change introduces extreme new temperatures and highly volatile weather patterns, the question we have to leave you with is, how will our recipes for flexible and rigid pavements have to evolve to survive the next century of travel?